We're going to finish off substitution today. The first little joke here says there are only, and they got this integral kinds of people in the world. Those who know calculus and those who don't. Let's look at how would you solve this integral. Now it looks kind of complicated. Maybe we have to use some substitution, but actually on this one we don't. If you think back about what we know about this term, another way we could write that is x to the 1/2 power. If we have a single term in the denominator, then you can just simplify this integral by going through and dividing each of these by x to the 1/2. So this integral would turn into 52. If we divide x to the 7/2 divided by x to the 1/2, remember you subtract exponents when you're dividing, so that would be x to the 6/2 or 3. The next one, if we subtract it same way, would be 5/2 minus 1/2 would be 4/2 or x squared. The last one would be 3/2 minus 1/2 or 2/2, which is the same as x to the first. It's a much easier integral now to simplify. Let's find the antiderivative of this one. So if we go up a power, it would be 4. Reciprocal would be 1/4 times the 52 that was already there. Here would be x to the x to the third. Reciprocal is 1/3 with the 66 that was already there. Same with the last one. And we want to evaluate these at 1 and 0. Before we plug in the 1 and 0, let's do some simplifying here. Half of 22 is going to be 11. Here, a third of 66 is going to be 22. On the last one, 1/4 of 52 is going to be 13. So now we want to plug in 1 and 0 and see what we get. If you plug in 1, this is just going to be 13 minus 22 plus 11. If you plug in 0, it's going to be 0 minus 0 plus 0. Simplifying further here, we would end up getting 2 as our answer. So now you can kind of go back and read the joke again. Joke would be there are only 2 kinds of people in the world: those who know calculus and those who don't. So the bigger idea I want you to take from that one is that you can simplify integrals when you have one term in the denominator. We're going to look at one last type of integral today that we've kind of done with indefinite integrals, ones like this. If we were doing this with the substitution problem, in the past we would have said, oh yeah, we got that square root. We want to put what's underneath the square root equal to our u. Well, we can do that, and derivative here would be just 1. So making our substitutions over here, this would turn into square root of u. Our dx would turn into a du. Remember that we need to also change our limits. So we have 1 and 6 right now as our limits. We would have to change those. So if we plug 1 into here, we get 4. So our new lower limit would be 4. If we do the same thing with our upper limit, we would get 9. So that would be our new upper one. But the problem on this one is we still have this x squared. Now we did some of these before. Recall, when you still have some x's left after your initial substitution, what you're going to need to do is play around with your substitution and solve for the x. So if we were to solve for x on this one, this would turn into x equals u minus 3. So what we want to do is take that and and substitute that in place of the x here. So finally, our integral would turn into u minus 3 squared over square root of u d. Now this doesn't maybe look any less complicated than what we started with, but it is one that's a lot easier to simple, not a lot easier, but one that we can simplify, whereas the first one we couldn't. So to finish this one off now, let's simplify that numerator. U minus 3 squared, we can evaluate that by multiplying u minus 3 times another u minus 3 and foiling it out. So if we did that, that would be u squared minus 6u plus 9 is what that would turn into. On the bottom, we got that square root of u. Again, we know that's the same as u to the 1/2. Well, now similar to that problem we did from the joke, or the little saying on the first slide, is we can divide all these by a u to the 1/2, and then it's an integral we can simplify. So going through now and dividing each one by u to the 1/2, we would get, again, you subtract exponents. 2 minus a half is going to be 3/2. 1 minus a half is going to be 1/2. And this last one would be plus 9. Now here there's nothing to subtract, so if you just think about moving that up to the numerator, it would be u to the negative 1/2. That is one we can find the antiderivative of. So now add 1 and do the reciprocal of all these. Be 5/2, reciprocal is 2/5. The second one would be 3/2, reciprocal is 2/3. The next one would be 1/2, reciprocal would be 2. And we want to evaluate this at 9 and 4. Now plug in 9 and 4. I suppose we probably should do a little simplifying here first. 6 times 2/3 is going to be 4. And 9 times 2 would be 18. So now plug in 9 and 4, and we should be able to do this. When substituting in here, now you could kind of think of all these, if you wanted, as separate ones that you're evaluating. So for example, you could just evaluate this one at 9 and 4. What are you going to get when you plug in 9? Minus what do you get when you plug in 4? Same thing on the next one. What do you get when you plug in 9? Minus what do you get when you plug in 4? And let's do the same with the last one. And if you go through and simplify this, now you get it. Now remember, when there's a 2 in the denominator, especially like this one, we know u to the 1/2 same as square root u. So a 2 in the denominator here is like a square root. So these actually aren't too bad to evaluate here. This one, square root of 9 would be 3, square root of 4 would be 2. The next one, it would be like taking square root of 2, except then you just got to cube the number. So square root of 9 would be 3. 3 to the 3rd power would be 27. Here, square root of 4 would be 2. 2 to the 3rd power would be 8. Similar on the last one, or this, actually it'd be the first one here. Square root of 9 would be 3. 3 to the 5th power would be 243. Square root of 4 would be 2. 2 to the 5th power is 32. And so now you can figure out what the answer would be from here by using your calculator. So if we would plug that in, we would get looks like the answer comes out to be 26.5 0.4, or if you had that as a fraction, that would be 132 over 5. Either one of these answers would be acceptable because it's the exact answer. All right, so the big key on that one, if you do some of these substitutions and it's a monomial or one term on the bottom, look to simplify. All right, why don't you pause this little video here, see if you can try this one on your own. All right, let's see how you did at least setting up the problem. Here you want to put u equal to x minus 2, making our substitutions then. This would turn to our u. Dx would turn to du. It still leaves us with that x squared on top, so you would have to also figure out what is x equal to here and substitute that in, which would be u plus 2. Also make sure you do change the upper and lower limit here. It would turn to 2 and 1. Now as you simplify this, our u plus 2 squared, you'd have to FOIL that out. You get u squared plus 4u plus 4, and then divide each of those by our monomial term of u. And you should eventually end up with this integral now that you want to solve. So why don't you pause the video again, if you didn't get to that point, see if you can evaluate this and see what you get. All right, let's see how you did. If you kept evaluating this one here, antiderivative, pretty simple with these first two. This one, you got u to the first power in the denominator. That one would change into natural log, 4 times the natural log of u. Then plug in 2 and 1 for all the u's where you're finding the difference here. And since these are 3 separate terms, you could go through and do them all separately like this. Evaluating, pretty standard with the first two. With this last one, ln2, we can't simplify that to a whole number. ln1, though, recall, is equal to 0. So if you keep simplifying down, looks like exact answer would be something like this, 11 halves plus 4 ln2. And we can't really simplify that more without getting decimal number. So the big key on that one, on those substitutions, if you have to make a substitution, you want to try to get a single term in the denominator. All right, last one. Can we use the definite, can we evaluate this definite integral using substitution? Well, it sure appears very similar to the last two, but this one we actually can't. Why would we not be able to simplify this one? Similar to some of the other ones that we've looked at so far, remember when you're doing these, big thing is to check the denominator. Where would this one have an asymptote at? Looks like at x equals 4, which means if we're trying to evaluate this one from 2 to 5, would that pass through our asymptote of 4? Yes. This one we can't evaluate because it's not a continuous function. It's not continuous on the interval that we need to evaluate it at 2 to 5. So always kind of have that in your head while you're doing these, especially when there's a denominator. We need continuous functions in order to be able to evaluate it and get the correct answer, because we're finding area. If you got something like an asymptote, you're not finding the correct area. So what I want you to do is try out 6 of these problems and see if you can evaluate them with some of the substitution.